In Theorem 1.2, we're supposed to show that if functions f and g, f goes from a to b and g maps b into c, if those two functions are bijections, then their composition is also a bijection. And the inverse of the composition is the composition of the inverses, but in reverse order. So, we're going to leave the first part for the reader to do and focus on the second part. So this is the part that we'll be trying to demonstrate. We will start by taking this part right here and applying it to a point. First of all, let's think about where this point is going to come from. If this is A, and this is B, and this is C, so here is A and B and C. G composed with F, F goes from A to B, so this is F, and this is G. So here is G composed with F. And the inverse would go the other way. So the inverse would be this map right here. And at this point we can safely assume that both the composition is a bijection, so it will have an inverse as we'll have a function inverse, and we'll just denote it like this. The trouble is, whenever we use this kind of notation, we usually switch to g of f of x. But when we have this notation with the inverse on the outside, what are we going to do? We still would like to be able to switch back to g and f, or maybe g inverse and f inverse, but there is no rule for how to do that correctly right now. So that's what we're trying to come up with, is some kind of a rule to get rid of these parentheses and be able to apply g and f, or g inverse and f inverse separately, because we know how to do that. The next thing we have to consider is, what does it take to show that two functions are equal? To show that two functions are equal, we're looking at this function right here on the left and this function over here on the right. To show that they're equal, we need to show that every single element of C gets mapped to the same place regardless of which function is applied. So they act the same way on every element of C. So what we must show is that for any element, I'll call it little c of C, the function g composed with f inverse applied to C gives the same result as f inverse composed with g inverse applied to the point C. So if they act in the same way on every single element of C, then the two functions are equal. So what we're going to do is we will say, we have no idea what this is, but we're going to give it a name. So I'm going to call this A. In other words, C gets mapped back to A. By this function right here. And since we picked a generic point C, whatever we show for this point will apply to all of these points over here. So what we have to show is that this is also A. Want to show that this is also A. Alright, so now what we have to do is decipher what this means. So let's take a look at this. G composed with F inverse of C is equal to A. Well, what does that mean? That means that G composed with F of A is equal to C. But this means that F of A is equal to G inverse of C. All right, let's stop right here because at this point we may not be sure we know where we're going with this. And let's work with this separately and see where that takes us. We know that F inverse composed with G inverse applied to C is equal to F inverse of G inverse of C. But now take a look at this. We have G inverse of C over here and G inverse of C over here. This will allow us to substitute and say that we have F inverse of F of A. But what does that equal to? That's equal to A. Now take a look back at what it is that we wanted to show. We assumed that this was equal to A and came up with this condition that arises from that. And then we manipulated this side over here because we really wanted it to turn out to be A. And based on the fact that this is A, we were able to conclude that this is also A. So if this side is A, then this side is A, and the two functions are indeed equal.